Okay, so after a little bit of technical problems, I'm ready to start my presentation. So I will give you an overview of the technical overview of the things we have managed in here on the front of verification of quantum cryptography. So we'll cover several aspects, none of them in extreme depth, but I hope to give you an overview and also in particular an overview of what things are still work in progress or not even started and so on. And feel free to interrupt with questions because this is a informal dynamic setting. I mean, I made slides, which I usually don't, but someone felt like it today, but I'm open to deviate from what I'm doing if there's some interesting question. So first, let me talk about why we want to verify security in the first place. So when we have, the whole point of this is to run cryptographic protocols, because cryptographic protocols, they are kind of everywhere nowadays. We use them even without noticing in daily life. And the problem with cryptographic protocols is that they are quite ubiquitous. So we have them all the time, but they also have a high cost of failure. So if there's a little problem in there, it's not just that the device crashes. It even a small mistake can leak a lot of your personal data or even make you unsafe. And security bugs have one particularly annoying property, namely that they kind of want to be exploited. So a normal bug, you need to be unlucky not to run into it, or if you run into it, then maybe next time you just don't do the thing that activates it. But with security bugs, it's that there is someone who actually wants this bug to happen. So we need to be particularly sure that we have no security vulnerabilities in cryptographic protocols. And how we do that is by mathematically proving the security. I mean, that's kind of in cryptography the state-of-the-art way to do it. But there's the following problem. So in theory, we have that once we prove a protocol secure, it is secure. In practice, this is not necessarily the case. There are two reasons. One is that you might have proven a protocol, but then someone implements it and makes a bug in the implementation. And then the proof just doesn't apply to this protocol. This is a relevant thing, but not the aspect that I will be looking at here. And the second reason why proving the security of protocol may not mean that it's secure is that the proof just can be wrong. I mean, mathematical purists will then say, well, then you haven't proven it. But the thing is, we can't tell the difference. We write down a proof. People look at it, they say, oh, that's really impressive, nice new technique, and so on. But maybe on page 57, the variables x and y are confused, and because of that, everything is wrong. We don't know. And at least it's my personal belief that most cryptographic proofs are wrong. Not all, it doesn't always mean that the final result is wrong, but there's always something wrong in them. And how can we trust something which routinely has bugs in them? Because why would we assume that there are only bugs that don't break the overall thing? And to get rid of this problem, one potential solution is computer-aided verification. So instead of just writing the proof by hand and checking it by hand in particular, we want a computer to check the security of our cryptographic proof. This is a bit different. I mean, the aspect I'm looking here from automated verification, where we just tell the protocol to the computer and the computer is supposed to do everything. Here I'm focusing on the aspect where a human is still writing the proof, maybe with as much machine help as possible, but that's not the central aspect. But the machine has to check everything in the proof, so we cannot write wrong proof. We can fail to write a proof, but it shouldn't be possible to write a wrong one. So let me give you a very short idea of how cryptographic security proofs typically work, just to kind of set the scene here. I mean, cryptographers here will already know that, but I'll rush through it quite quickly. So let's say what we want to prove is that a function f is a one-way permutation, meaning, well, it's a permutation, which I assume is already checked and easy, but it's one way, which means that given a random output of that function, it is hard to find a random input. And now I define a second function, g of x, that is just f composed with itself. And now I could ask, is g also a one-way permutation? And now I will just show you how a cryptographer would prove that. So what we want to look at is this probability here, so we have the variable x picked at random from the domain of this function. Then we evaluate the function g on x. And then we call an adversary A, which may be an algorithm on input y, and it outputs some x prime. And the adversary wins when x equals x prime, meaning if the adversary has guessed correctly the input to the function. And now I want to show that this probability is small. And I just do this by rewriting what I have here a number of times. So first step is I could just insert here another line, I compute the value z. This will not change anything because it's just never used and it has no side effect. So the theorem doesn't change. Now look at this g of x. I can unwrite it as f of z because z is f of x, and g of x was f of x. So this also doesn't change anything. Now I can rewrite x equal x prime to f of x equal f of x prime because f is a permutation. Now I define a second program b, which is like a new adversary that just runs a and applies f to it. And then here, since a is so this y is no, that's the wrong element. So I can replace a of y that computes x prime by b of y that computes z prime, which is f of what originally y was. And then I update the formula here. Let's not go into all the details because it's very fast, but basically this is again the same. And then maybe I would say that picking x at random and applying a permutation to it gives me the same distribution as just picking at random, still the same game. And now what I have is just by definition the probability that B attacks the one-way permutation G. And this is by assumption, since F was assumed to be one permutation close to 0. And since it was the same as the probability that A attacks, we know that the probability of A attacking is close to 0. So this is how cryptographic proofs work. And it doesn't matter whether you got all the steps because it's just to give you the impression. So we know G is a one-way permutation. Now, if we want to state this like a little bit more formally, what we did here, it's a so-called sequence of gates. So this is the established approach how to do cryptographic proofs, and in this approach we write down the thing we want to prove as a little program, typically called a game in cryptography, and then we change this program in little steps. And in each step, we show that, for example, a certain probability is the same, or that the two games stand in some relationship after that step. And well, there are two questions that arise in this approach. One is, how do we even find the sequence of games? How do I find my mouse pointer? Ah, here it is. So how do we find the sequence of games? I can make it more visible. So how do we find the sequence of games? Well, the answer to that is that in the context of this talk, we don't ask this question. We just say cryptographers have to be clever and come up with the right sequence. Of course, I'm not saying this is the only way, but in this, I will not go into this question here. And then the second question we have to ask, given two games that are kind of in some way obviously related, how do we actually formally prove that they're related? I mean, a human may just look at it and believe it, but I've also seen humans believe wrong things about two consecutive games. So that doesn't mean much, but how can we tell a computer that two games that I've written down are related in the way I claim? And this is technically the main challenge that we encounter in formal verification of cryptographic proofs. So let me summarize what we have seen so far. So what I've shown you by examples is that cryptographic verification, the verification of cryptographic proof, basically boils down to reasoning about programs, which means we could use Qrihl logics, type systems, all these things to analyze them. And particularly it boils down to reasoning about the relationship of two programs for which there is something called relational Qrihl logics that we will have a quick look at in the following. But is there anything you would like to ask about what I've said so far?
From practical viewpoint, this easy group is one of those tools. Does it have nowadays a reasonable kind of description? How do you prove that? Does it have a reasonable kind of tutorial?
I mean, it has tutorials. I don't know if they're reasonable because I haven't read anything recent. So you'll have to ask someone who more recently got into EasyCrypt. We have at least one person in this audience who did that. I think the most recent one is Cut. Cut, do you think there are good tutorials for EasyCrypt?
Sorry, could you repeat the question?
The question is whether nowadays there are kind of tutorials that tell you kind of well how to get into EasyCrypt, or you kind of is one left alone when starting to use EasyCrypt?
I think there is enough resources to start, but I wouldn't say it's like the best ones that are there. But yeah, there are some materials to be used. Okay, so that's the answer I can provide by delegating. Thanks, Kat. Okay, so let me continue now with this. So I mean, we haven't reached the quantum part yet, but there's still like important background to be covered. So the next thing I want to tell you about is relational Qrihl logic, because this is at the very core of the, well, at least of the approach we use, also the approach that the EasyCrypt tool for classical verification of crypto proofs uses. And what you do with relational Qrihl logic is you describe the relationship between two programs. Or more precisely, you ask if the variables of two programs are in a certain relationship in the beginning. For example, here we say if x, which is from the first program, equals y from the second program in the beginning. And then we run these two programs. For example, we increase x by 1 and we assign y to z. Then we say afterwards the variables are again in a certain relationship. In this case, the relationship would be that x equals z plus 1, which is kind of intuitively clear because z is what y was, x has increased by 1, x was equal to y before, so now x is equal to z plus 1. But of course, you want to also convince the computer of these things and not just believe it. Also, how relational Qrihl logic is defined becomes actually relatively subtle once we go to the probabilistic setting. So in the deterministic setting, it's quite obvious what these things mean. Already in the probabilistic setting, there are subtleties one needs to handle. I mean, the definition is difficult, but probably you wouldn't get the right definition right on the first try. And in the quantum setting, it's even worse. Okay, so now I've given you kind of the setting in which we live, and now what are we doing here? So we want computer-aided verification of post-quantum crypto and of quantum protocols. So I distinguish these two things. By post-quantum crypto, I mean when the protocol itself is classical, but the attack is quantum, and quantum protocols is protocols in which even the honest participants exchange quantum messages. So, I mean, it's an important technological difference, whether you can run it on a normal computer or not. In terms of techniques, it's there is a lot of overlap in what you can do and cannot do. So there is no like really sharp distinguishing line around these two fields. And we want to have interactive tools for doing this computer-aided verification and automation where possible, although we haven't much on that front yet. But first you may ask, why can't we use just the same logic as in the classical state, as in the classical case? We have already things to reason for progress. Well, the thing is, you cannot just use the logic that is, for example, in EasyCrypt off the shelf, because the logic encodes things like specific to the nature of classical computation. For example, you can copy the state of some machines. You could fix some random coins in the beginning and so on. And these are things that you have no correspondence in the quantum setting. And EasyCrypt, I mean, I made an example proof, for example, at some point where I proved something that is just wrong in the quantum setting, and I could prove it in EasyCrypt because EasyCrypt kind of assumes that everything is classical. There is now some extension, I haven't studied it yet, there is some extension of EasyCrypt to cover also some quantum things in some to some limited extent, but I can't say much about it because I haven't studied that yet. Okay, so the project we have here is Qrihl Tool, which is a tool kind of similar to EasyCrypt, but specifically for quantum programs. And instead of telling you abstractly what it can do, I will instead just open it and show and do a proof. If I find it, here it is. So make it big. I'm currently trying to zoom to make the font size bigger, but I don't know how because the normal hotkey is gone. Okay, I cannot increase the font size, and I don't know why I cannot increase the font size because usually I can. So my apologies for that. I hope it is sufficiently readable what we have here. So in the tool, what we have is we first have some description of the things we're talking about. So I will look at the example of a of the quantum one permutation. So what I'm doing here, for example, I say f is just some function from a set type domain to the domain that is bijective. So I'm assuming it's a permutation, and then I want to show something about it. Then I have variable declarations. I will ignore them. Wait, this is the wrong file also. But I thought what I thought so far the lines were the same. And I'm not going to show you the whole proof of what I showed on this slide before. I will show you only one of the steps just as an illustration. So what I want to show is that, so I look first at this program here that says I pick x uniformly at random, then I assign z f of x, then I assign y f of z, and then I call them adversary. I'm not giving explicitly the inputs and outputs here because that is unfortunately not supported at this point, but instead I just say the adversary can access y and can also write into z prime. And I want to show that this is the same as when we replace the first two lines by this line here, where I just pick z uniformly at random. So this is just the setup, but the interesting part is the actual proof. So in this, what I say is the probability that z prime is the same in both cases. And how can I prove that? Well, first step is I want to So I want to use QRHL to show these equivalence of two probabilities. So I just use the tactic by QRHL, and you see in the goal window, it has now replaced it by something. Oh, here I can zoom here. By something that says if everything is the same, and I do the one program or the other, then the left winning condition holds if and only the right winning condition holds.
What does by you error mean?
It means I want to prove the current subgoal by using QRHL, so it replaces this subgoal by a subgoal, a quantum relation. Oh, I have never mentioned quantum relational logic yet. Yeah. So the logic we will use is similar to relational logic that I sketched, but a quantum variant. So
this CLA is
CLA means it's a classical predicate, what's written in the brackets, which is, I mean, the precise meaning will come later, but we have here stuff in the way. But basically, think of it just what in these brackets is here, that holds. I mean, that's a precondition and a postcondition. And now if I want to actually do this proof, I inline P1, I inline P2. Now the programs here, and now I kind of work my way backwards by backwards reasoning. So I can say, well, for this postcondition to hold, it is sufficient that we have all the variables of B are also equal before the call of B. So I apply a tactic that's called equal. That gives me that. It has one technical subgoal that I remove. And now you see I have removed the call of the adversary and need to show that after these things are related as I am writing them here. This is rather unreadable, but I can run it through the simplifier. And now it basically says all the variables are the same on both sides.
Just a stupid question. Why do you mean 3 steps instead of saying equal sim?
What, 3 steps?
So you have this tactic equal, then you have tactic simple, and then you have a tactic sim. So why can't I have just a simple tactic?
It doesn't say simple, it's sim because equal gave me 2 goals. One of them being just a technical thing about variables being distinct. So I used one sim call. It's actually sim exclamation mark. And now I can zoom. So I used that one to solve that goal. Exclamation mark means I want to get rid of it. And the second sim just simplified the current goal but didn't remove it just for readability.
Okay, but what I ask is that is there a cases where if you apply the equal to sim, the first goal is not trivial?
It should not. I mean, ideally equal should make sure, but the thing is that equal cannot fully guarantee it because the thing is, it's about the variables that occur in the term. Equal looks at the variables there, but it may be that they're hidden in definitions, so you could actually trick equal. And this is why you get the obligation to prove that you have not tricked equal. Yeah, but usually this should work without, if you haven't done weird things, or then it should just work. Okay, so now we can continue this proof. Now we have here assigning something to y, the same thing, and then we have assigning something to z. So we can use weakest precondition rules, make 2 statements on the left, 1 on the right, to further simplify our postcondition. And now we have a postcondition that says, I want everything to be the same, except this one is a bit non-trivial because it doesn't say, it is not the same as saying x1 equals x2. It's saying f of x1 should be z2. So we get suddenly a condition where we pick x and z randomly, but they shouldn't be the same, but they should be related by a bijection. So we need to tell the tool how to do that in a way that makes sense. And I don't want to go into the details of this tactic, but instead just write down the thing we can do there. I hope I got it the right way around. You can simplify some more. And now we have the empty programs. So basically all we need is that the precondition implies the post condition. And I think simp will show that. No, it didn't. Oh yeah, this should be an X. Still not, maybe the F was on the other side. Okay, I thought I can do it without much thinking, but apparently I made some mistake. Ah, yeah, obviously. I forgot one thing. So this was correct. However, we do need to use somewhere the fact that F is bijective in this, which we can use here, and it still doesn't work, and I don't know what I messed up. Sorry. I have no clue what the difference is between
one shift missing between the random shift.
Yeah, but that shouldn't change anything. So I'm not sure where I made the typo. And I don't want to go into it, but basically what I told you is working. And this also shows like how sometimes you get stuck with something which should be completely obvious. Like you have two exactly equal things, and one of them works, the other doesn't. How can that even be? Probably there's some tiny difference somewhere where I made a typo or something. And that can be sometimes very annoying, but that's something that is common to all kinds of verification. So this was a short demo about how you can use this tool. I will come back to it. But what we have seen in this tool, yeah.
So you by how other people make mistakes and proofs and so on. How do we know that people didn't make mistakes when they programmed this Isabel thing?
Exactly. So so the question was, how do we know that the programmers of the tool don't make a mistake?
Yeah.
And that's actually a very valid concern. And the best approach we have for this particular concern is what's often called the foundational approach. So that you would say, we do not write like high-level tactics. Like, for example, we don't write something like by QRHL, which just is programmed to do the right thing and manually proven, but instead, even by QRHL would call some theorems in Isabel, and Isabel would write down every of these theorems into very elementary proof steps. And those elementary proof steps could be given to a very simple program that checks everything from scratch. So we are not there yet, but the goal is to actually get there. Of course, it could still be possible that the independently written proof checker has a mistake, but the probability that there's an exploitable mistake there will be quite small, because we the mistake has to be kind of independently still match the bug in our proof, and it has to be a mistake in a rather simple program. Yeah, so you can never be totally sure, but you can make it quite unlikely that there's a mistake.
Can I ask the user perspective question?
Yes.
So you showed the proof and it contained very fine-grained steps.
Yes.
Can you get rid of those steps? Because
you want automation, basically.
Not full automation, but I want, okay, you said that okay, there was this simple explanation which should always work unless there is a problem. So what I would like to have is that I would have proof steps for some which would work, or if it kind of fails, tell me, okay, what was wrong.
Yeah, I mean, there are two aspects of it. One is about the can we make that there should be less proof steps, and I'm not sure this makes the usability actually bigger, because you just have a goal, you do simp, it's done. So it costs you writing just simp, and this is an extremely small cost compared with the
cost of figuring out things that are wrong. So I think having this, that it automatically removes that goal, wouldn't really increase the user experience practically. But the other thing is about doing something and trying to tell you why it went wrong. I have done that actually with the equal technique. The problem is that the reasons why it cannot be applicable can be very complex. So I'm not sure I can. Well, I can try to make a wrong. Okay, I don't know right now how to make something go wrong here. So
I would just concentrate on these 3 lines which you have: equal, sim. Okay.
Yeah. Yeah, it does equal. Yeah, I mean it does give you the whole reasoning here. So it writes a whole novel about the different conditions it checks and so on. So if something goes wrong, you can read through this and you will exactly find out what went wrong. The problem is this is kind of several pages of text of human explanation.
Okay, and it's not in terms of a program trace that, okay, this thing would happen, but it's something like unintelligible.
It's about applying the equal tactic. So there's a proof of the equal tactic in the paper, which is like there's a rule and it has like, I don't know, 20 or 30 conditions about 3 variables being here or there or something. You cannot give a trace here because it's just unknown code. Yeah. So that's the best I can come up with, but I think removing the sim exclamation mark here would not really make any drastic difference. I mean, I could do it, it's a matter of taste, but then you might get an error in the rare cases where you could prove it, but only with some extra thinking, or you could make it dynamic, like sometimes it appears, sometimes not, which makes the proof more unpredictable, because what if it changes that there's an additional subgoal? So that's why I just put it there and left it there. Okay, back to the thing here. So now this quantum relational logic. So in what respect was what we had actually different from something classical? We didn't really do anything non-classical here, but actually if you look, the subtle thing is this CLAR, because the pre and post condition actually are not Boolean predicates, but something else. So let me tell you a bit about this quantum relational logic, and then we will look back at the tool to see where it popped up. So in quantum relational logic, we can have not only classical variables, but we can also have quantum variables, which in our example we did not involve, but we could have. And then you could have programs like if I apply a unitary u to x, or I apply a unitary u to y, or something like this, and I could say if x and y are equal before, then they're equal afterwards. But the crucial difference is that the predicates, they are now not Boolean predicates anymore. They are subspaces of quantum states. So every predicate here is a vector space of quantum states that we consider to satisfy the pre or post condition. So because we have quantum variables, so we look at the states of all the quantum variables, and we say this state is before the program in this subspace, after the program in that subspace. And we then need to show that this pre and post condition thing, that they're related in that way. So this is, you could ask, why does it have to be subspaces? Why not just set of states? The answer is because subspaces behave really nicely and other things do not. I'm not saying it's impossible, but I found it that this is the right choice. But now you might ask, well, we just saw this thing which was supposedly done in Qrihl, and I never saw any subspaces. Well, that's because I was hiding the subspaces for you behind syntactic sugar. So if you look at this thing here, this is just a Boolean expression. Okay, you don't see the highlight. The thing inside the square brackets
is just a Boolean expression, so it's true or false. And then I have this constant cla, so that cla of true is the whole space and cla of false is the zero space. So I basically translated a Boolean formula of classical variables into something expressed as a quantum state. So we have not involved any quantum variables, but we can just construct a state that's always true or always false, depending on the classical variables. And that's a nice trick to have predicates about classical variables. And if we have only classical variables, then everything we see will just be of the form cla of something, and that's it. And basically, we have just reproduced classical relational logic. But I don't know, before I come to cases where we actually want to use, where we actually use something non-trivial instead of just cla, let me show you the definition of QHL, or sketch it to you, so that you have an idea how one even defines such a thing. Because what we need to say is that if something holds before and then we run two programs, then something holds afterwards. But it doesn't work as easily as just saying I take any state that satisfies the precondition, run the two programs on the two halves of it, and look whether the postcondition holds. Even in the probabilistic case, that gives us a bad definition. For example, say you have a wait, let me open my writing thing for that. So let's say you have something like, you say that x1 equals x2. You have two variables that are the same. Or actually, I don't care what's in the precondition. But then I say x1 is applied a random value, let's say uniformly. And in the other program, we apply uniformly x2. And I want then x1 to be equal to x2. If I just see these as two programs that are just run independently, the probability that the outputs will be the same will be, well, at least not close to 1, unless it's the set of values I picked from has just one element. But I actually want things like this to be true, because it's the same program. So I would want them to do the same, or to be considered as doing the same, even though if I run them independently, they might not. So I want actually a definition that encodes that that I will have x1 equal x2 if I run these two programs somehow in lockstep. So for example, if they both pick randomly, they would have to pick randomly, but the same. Like looking at each individually would be uniformly random, but it happens to be the same. And this was achieved in probabilistic relational logic, and we need to do the same also in relational logic. So how do we do that? Well, what we do is for any quantum state that satisfies the precondition, so for example, something which has variable x equal y, and then I apply those two programs to the marginal, like to the state describing the left system and the state of the right system. I mean, I quantify over quantum state of the whole one, but I can kind of project them onto the marginals. I apply the programs to the marginals, and now it's not that I ask that the product state, so just putting them back together, satisfies the post condition. No, what I ask is there exists some state of the final system that has those final states as marginals. So I'm allowed to put those states together in any way I like, as long as the projections are what I want. So this is not so easy to wrap your head around why this is the right thing, but this is also analog to how we do it in the probabilistic case, and it works well, except in the quantum case it doesn't, unless I add the word separable here. For technical reasons, there are rules that we cannot prove without this, but there is no intuition for that. Yes?
Just a question. So the separable comes only because if you have infinite quantum.
No, it is needed to get the equal rule, for example. or was it the frame rule? I don't know, one of the rules, we don't have a proof without that. And it's not about whether it's finite or infinite.
At least in functional analysis to separate.
Separate, it's a different separate. You are thinking of separable Hilbert spaces,
yeah,
which corresponds to the Hilbert space having countable dimension. Here, separable means not entangled. No entanglement between the two memories. Within the variables in one memory, yes, but no entanglement with the two memories. So it's completely different meaning of the word separable than in the term separable Hilbert space.
Okay, but if you say that there are no entanglements between different programs in one, is this a trivial thing to consider? Meaning that it's trivially holds.
No, you can't say whether it holds or not, because there is no such thing as the two programs never run in the same world. They are separate, so you cannot ask whether two programs that have never interacted have joint randomness, because it's just a hypothetical construct here.
But okay, it is just a formal statement that okay, these programs run in a different world.
But they don't fully run in it. I mean, there is no operational meaning of this, because it's not. I mean, they can be statistically, probabilistically correlated, the initial states, but not entangled. It just happens to be the rule.
And so physically, they are just separated, right? So you can't do just an entanglement.
Yeah, okay. But they don't really run in one world, because what I'm doing here is it's not that I make the state and then I run the two programs. I make the state, then I take the marginals, and on the marginals I run the two programs in completely separate worlds. Well, what does it even mean? I mean, there's and then I can put these marginals together in a completely different way. So there is no physical meaning of this.
Is it easy to come up with two programs such that this separable thing doesn't hold?
It's not a property of the program. What do you mean that with coming up with? It's just the quantification of the states.
Okay, yeah, but this means that I can always assume that they are separable, and that will be done.
What does it mean you assume? Who is separable?
So okay, so is there a reason to add this condition, because it's
yes, because otherwise I cannot prove the rules.
Yeah, but okay, is it possible for me to formalize a condition where this thing doesn't hold and it's a natural? This is what I'm asking.
So you mean I mean, I'm not sure what you mean by it doesn't hold, because it's an old quantifier. So I mean, but it might be possible. I think there are examples, I don't remember that, of programs which satisfy the definition of Qrihl judgments which satisfy one of the definitions and not the other.
So there are two exist like non-separable artifacts.
Well, that definitely, but that it could still be that it's not relevant for this definition. But it's not a property of the programs. That's the point.
Okay, so it's a property of the relation before and after.
Yes, that one is, or it's a property of how we interpret that relation. Because the relation is just some set of quantum states, which could be entangled or not, or whatever. But we only consider them applied to separable cases, and on these separable cases, we do our analysis.
And it still leaves out and doesn't say that does it make sense for me in some context.
It does make a difference whether we allow them or not, because if we would disallow them in the predicate, then it couldn't be a subspace, because the linear closure of separable states gives us non-separable ones. So, but you can, if you would see this not as a subspace but as a set, then you could see it as a set of states where you're only allowed to put separable ones in. But it would give you a not very nice mathematical characterization of what the predicate is and what not. Okay, so that's the definition. Yeah, and we need this frame rule that allows us from modular reasoning. I mean, I can't explain you why we need it, because somewhere deep in the proof, I need to decompose states in ways that I didn't manage to do. I don't even have a proof that it doesn't work. I just didn't get it to work. Yeah, so now comes one of the most, well, probably one of the most confusing, but also of the most important aspects of QRHL is how do we write, what does it mean to say that two programs are equal? I mean, I had it already in this example here, but I didn't say what it means. So we need to give a meaning to two quantum variables have the same state. And that's not as easy as it might sound, because we cannot talk about the state of one variable. It's not in the classical sense. You can ask, like, what's the content of X? And the answer is something like 5. And then I ask, what's the content of Y? Answer is 5. Aha, same. But I cannot ask what's the content of this quantum register, because it may not have any meaningful answer what the content is. So in particular, we cannot express it as a Boolean formula. However, there turns out to be a nice, a reasonably simple definition of quantum equality as a subspace. So it's not, this thing is not a Boolean expression. This is a subspace, intuitively the subspace of all states where x1 and x2 are equal. And I define this space by just saying psi satisfies this predicate, meaning psi, the state psi is in this subspace, if and only if the state is invariant over swapping the content of those two registers. In the classical case, this is obviously exactly what it means to have the same content. If I swap two things and this overall thing state stays the same, it's the same as saying if I read them, they are equal. In the quantum case, I can come up with quite a bunch of different variants of the notion of equality that are all different, and they all don't behave as nicely as the classical equality, but this one is the one that seems to work best.
So just to understand, if x1 is somehow entangled to another variable, so then they are not swappable.
They could be. I mean, for example, take the so-called GHZ state where we have 0, 0, 0 and one in superposition with 1, 1, 1, and now I can swap first and second one and still get the same state. So they would satisfy the quantum equality. However, there's suddenly combined with this thing that that we want separability between the left and the right memory, and typically we apply quantum equality to left stuff equal right stuff. And there we have the condition that they cannot be entangled, at least, but not by definition of quantum equality, but when we interpret it in the QHL content. And their quantum equality effectively implies that something that is equal to something else is not entangled with anything else not appearing in this quantum equality. But that's not by definition. That is an emerging effect from the quantum equality together with the QHL definition.
I mean, so if this x1 equals x2 is just by something a subspace, so this proves that we have a subspace, and then after we do these operations, we still have a subspace, but like, is it the same subspace or like, or what?
But in this case, I mean, the equal rule says if I do the same, if like all the variables, so x1, x2 refers to all the variables of the program C in this specific case. So if I say all the variables on the left equal to all the variables on the right, and I run the same program, then all the variables on the left are equal to all the variables on the right. So it means
I understood that this being equal is just actually a true statement. It's just like a description of the subspace.
yes, exactly. So if I start with something in the subspace of things where left and right have the same stuff,
Yeah.
And I have the same program on both sides, then I get the subspace where things are equal on the both. Then I get a state that's in the subspace of things are equal on both sides.
So is it the same subspace as both parts?
It's the same subspace, yes.
Okay.
Because the subspace is defined by the formula. So the formula is just some syntactic stuff for describing a subspace. In this case, the subspace described by this definition here. So predicate is always a well-defined subspace described by some formula, potentially using some fancy syntactic.
Doesn't it always know that that I have some subspace on that path, then I do some program, and then I have some other subspace.
Well, technically, it doesn't always help, but if these programs are terminating, then yes, there will always be some subspace that you are in the post condition, but it may not be an interesting one. I mean, it's like saying if I run a program, there will be always something that holds afterwards. That's true. I mean, true holds after running a program, but I want to know that something specific holds. For example, it holds that the variables are still the same.
It just seems intuitive to me that then this try would be written somewhere.
Sorry?
What just seems intuitive to me that you would note down this try somewhere in this precondition or this.
No, I mean, I have a concrete space, maybe the space of things where x1 equals x2.
Okay.
And that is the subspace we are talking about, concretely.
Okay.
I mean, I have defined the subspace.
Okay.
Like this equal symbol is defined as the subspace invariant underscore. Okay, so yeah, so that is the quantum equality. Details are a bit subtle. Most of the time, you don't need to understand. You will not use the definition, but just various properties of it. But let me show you how the quantum equality actually comes into play in Qrihl Tool, because we didn't see any quantum equality. So why is it relevant? Well, the thing is that in this thing here, we proved something kind of a bit boring. We proved we had a game where we had these games only involving classical variables. Well, that's okay if you do post-quantum crypto. But we also had an adversary that involves only classical variables, because I explicitly listed the variables of the adversary are x and are y and z prime. These are declared as classical variables, so this adversary is by definition classical. Now let's make it a quantum adversary. So let's declare a quantum variable state of some type infinite, which is just some infinite type. And let's say that the adversary also can access this variable, which effectively means now the adversary is a quantum computer. It can keep a quantum state. We don't change these programs. We don't change the thing we want to prove. But now we want to prove, now we effectively prove this for all quantum adversaries B. And now let's see what changes. So by Qrihl will not change much in the post condition. There's a change in the precondition, but I will only look at the post conditions in my explanations. Don't explain too much. So things are pretty much the same up to here. But now if I run the equal tactic, which removes the adversary, what I basically need is for this post condition to hold, here, I will need that before the adversary call, all the variables of the adversary are equal. And this is what the equal tactic will actually give me now as a new post condition, if I clean it up a bit. So you see, here is some classical stuff wrapped in a clar that basically says everything is, all classical variables are equal on the left and the right. This clar thing makes this a subspace, and this subspace now is intersected with the subspace that is this quantum equality that says state 1 equals state 2. So here we have a true quantum predicate, not a particularly deep one in terms of what's happening. It's just an equality, but actually equality is a non-trivial thing here. And we need to, and this is how simple post-quantum crypto proofs will always look like. They will just carry an equality of the quantum state of the adversary, but never touch it. So this is kind of the simplest case. And in this simple case, actually the proof that we had just works as it was before. The post conditions kind of keep having this equality, but the simplifier just manages to get rid of them. So now we have made it into a post-quantum crypto proof by involving quantum equality. Yes, Thomas?
I guess one qubit, or if they have only one state.
But it's an infinite variable.
Oh.
Yeah, so I can use a type. I mean, infinite is not particularly specific. I just declared this type. I could also have said string, then it would be quantum strings. I could also make something concrete. I could say 60, like 1 million bit words or something, but giving it an infinite state is kind of covers all bases. You could give it more variables. It wouldn't change the proof. It wouldn't, but it would mean that the post condition suddenly will now list all of them. Like if I make, I don't know, quantity.
Dominic,
Yeah.
if you never use that state, so why bother?
Because of soundness, because I want to, because the logic, I mean, the adversary might use it to keep maybe some information between different invocations and so on.
But why bother? Why can't we just take the easy proof and weed out some of the proof tactics which are not kind of applicable anymore, and then say that, hey.
Yes, we can. If we do just that, we get something that manages all the very elementary ones, where we don't have to worry about anything. For example, random oracle model, you will already get stuck. Then reminding, you will also get stuck. Then you could extend it some more, and because I think that's what they have done in this extension that I haven't studied yet. You could make like hard-coded support for particular cases, like calling random oracles and transforming random oracles, but you will not get something generic. And in this case, for this particular case that I showed you here, yeah, that would work. For something, for other things, it might not work. And this is, for example, my next example is something where the quantum equality is suddenly interesting. So the program I have here is I'm having the left and the right program. Both of them initialize the quantum, the qubits QR jointly as an EPR state. So I take that now. The first program applies a Hadamard gate on the first variable. The second applies on the second variable. And what I'm claiming is that these two programs still lead to the joint state being equal on both sides, even though we did different things. But an EPR pair is such that if I do different things on, like if I apply Hadamard on the left or on the right, that will give me the same result. Yeah, so I can do these things. I don't want to go through the details, but basically it's, yeah, it gets already some more complicated thing. It's the quantum equality of these things, but that subspace now multiplied with the Hadamard applied on the first variable on Q1 and multiplied with the Hadamard on the second one. So I can multiply, I can apply unitaries to subspaces. That just means applying it to every state in this space. And then I can do more steps. And what I get in the end is something kind of a bit weird looking. This I can actually prove by using a lemma final goal that I've simply shown separately in Isabelle. So here I've just copied it basically, or something very similar. And since we have just a 16-dimensional system here, actually Isabelle can just solve it by explicitly computing all the involved matrices. So I didn't actually need to think how to prove this. It's just by explicit computation, and this solves this goal and done.
I have a question.
Yes.
So let's say we have a proof here that, for example, that formal world that Elgamal is secure.
Yes.
And then we like give the adversary a quantum state.
Yeah.
So how does the adversary know that they use this quantum state to break Elgamal?
I don't know how it knows it, but it would just, I mean, there exists an adversary that breaks Elgamal by doing naughty Shor's algorithm stuff. So it exists,
Yeah.
but it only exists if it has a quantum state.
Yeah. But how does?
No,
I mean, all quantified adversaries just know how to attack. You don't need to tell them.
Thomas, this is in a way that you can't even define that, that you have a deeply Hellman group in quantum static.
Yeah, I mean, or you can say differently, like if you, for any concrete group, the adversary can break it by using close algorithm. Yeah. I mean, the reduction proof is still correct, but it's it reduces one false thing to another false thing.
This is interesting, Dominic. If you, okay, in order to do this 4 algorithm or whatever, you need a certain number of quantum bits. So is it actually possible to state that you can't do this LML because, okay, the quantum computer goes up, meaning it becomes bit coherent, and that shows that other disassumption with the LML.
So you mean, yeah, I'm not aware of research in that direction, but maybe it is possible to, because I would kind of very strongly guess that if I, for example, 1 qubit, I cannot build a quantum computer that breaks Algamar from it. Okay, that should be easy to prove because I can simulate 1 qubit. So for logarithmically many qubits, this does hold because I can just simulate them on a classical computer, and then I have a reduction to a classical one. But I don't know any results that are like on the in-between case. And definitely I don't know anything related to QHL related to that. And I don't even know anything about it in the just pen and paper world.
Okay, just one question of curiosity.
Yeah.
So, okay, you said that, okay, there are post-quantum proofs which are non-trivial.
Yeah.
Meaning that they have to deal with the quantum state.
Yes.
So what are those related to rewindings or what they are?
They could be related to rewinding, they could be related to random oracles, they could be related just to quantum programs, quantum protocols that actually center on quantum states. Yeah, so these are kind of the main candidates for that. Okay, so this is what I wanted to say about the Qrihl tool and the logic itself. So now let me tell you a bit of the various other related things. So one thing is the first and actually only finished major analysis is a protocol by a variant of the Fujisaki-Okamoto protocol, which is used in many of the NIST post-quantum crypto candidates. We have an analysis of this. It is in places not very pleasant because there is not much support for modularizing things. So this is something that definitely needs improvement, but it is possible to do a non-trivial proof. I don't want to go into that, but I will tell you a bit about the various challenges I have encountered. So when you do the proofs, you always get these verification conditions. So relationships between some precondition and some post-condition, like for example, one subspace, typically it's something like this subspace is a subset of that subspace. So this is how they all look like. But in these things, we typically have something like, oh, now we apply a Hadamard or some operation to this variable and one to this variables and so on. And you get these expressions that talk about like operators applied to some variables that may not even be next to each other. And actually reasoning about these things is quite cumbersome formally. Like intuitively, we have a clear idea what, for example, this thing is, C0 xy times C0 yx, because it would just be, I mean, I just can, wrong button, sorry. I mean, it just means I draw several lines and I draw this and maybe this. I mean, I'm not sure the thing was on this slide, but I just draw quantum circuits. But if you actually formalize them and have things like I apply one variable to some one operation to 2 registers, then I actually need to kind of swap them first to get them in the right place formally and so on. So it's actually a bit hairy to work with. There are some ad hoc things to make this better, but I'm the current version is very cumbersome to reasonable form. The second challenge is working with the quantum equality just because of some inherent weirdnesses of it. For example, x1, y1 being equal to x2, y2 is not the same as saying x1 equals y2 and y1 equals y2. These are different things. The latter one, yeah, exactly. The latter one is this. In this case, it's an implication, and well, backwards. No, in the classical world, it's the same. If you have a pair of values that are, if your pairs are equal, then the components of the pairs are also equal, and vice versa. No, it's not multiplication. Sorry, this means I mean, if I write quantum variables next to each other, I mean like it's basically like pairing, except you can't define it as pairing because pairing operates on values, so it's a classical concept. Yeah, there's no automation for common tasks. That's also one of the challenges I encountered. There was lots of copy and paste, which I partially made better by writing scripts that do it, but that's not really an ideal solution. But let me talk about some of the solutions. Well, for the copy and paste down here, some nice module system would be nice, but it's something, but it's not even started. More interesting in the context of current work is the this working with variables, because I developed something which I call the register formalism, in which I can treat variables, quantum registers, kind of more abstractly as mathematical objects that I can reason about. So instead of saying maybe variable x is just the 17th component in this thing, I can abstractly say what is a variable that talks about, like what is a register referring to some place in the quantum memory. And then I will be able to see all these things here as different instances of this concept. And I believe this will make things considerably better to work with, but that's still work in progress. But let me tell you a little bit about this register formalism. So what it tries to answer is the question, what is a quantum register? At first, this seems very simple because quantum register is just a line in a quantum circuit, or if you have a tensor product, it's just one of the factors, but that's a very limiting definition. Because, for example, if you have like a quantum system that is like x tensor y tensor z, then x and z together are not a register. It's kind of like a sequence of registers. Or if I have x tensor y tensor z, and z is a multi-qubit thing, I cannot talk about the 5th qubit of z or something like this, because it's the formalism is just restricting us to say it's, so when I compose the system in the beginning, and that fixes what are the registers I can talk about, and putting two of them together is not a register, and so on. So yeah, here's for example the example if x and y are registers, x, y is not, and all these things make it very hard to read. So the solution is an abstract notion of some part of a register. It just means some part of the memory, which does not have to be in any way kind of consecutive or something. And then it would be that, for example, x and y also fits that definition, and I can reason with it kind of more smoothly. Or I could also say if x is a register, sorry, there's a typo, let me fix it. Okay, I talk because it's making the way. So if I have x dot z, could be like if z is a register, like a part of a smaller memory, namely the memory that is the content of z. So I could have a register that refers part of the content of another register. So I can change that. Like imagine z means the 5th bit of a 5-qubit system, and x is a 5-qubit register. Then x dot z is also a register referring to that. How do we define this? I mean, that would be a whole separate talk, but I'm giving you the basic idea of how registers can be formalized. So we want to formalize a register. I lost the mouse point. Okay. Now I understand what I have to do. deactivated this. Okay, so I want to define what a register is. That is in some Hilbert space of memories, like we have our whole memory inside which it's located, and then we have the space that describes the content of the register. Yeah, so for example, this could be a qubit, and this could be like the whole computer. Or this could be a qubit, and this could be a 5-qubit system if it's like a subregister or something. And mathematically, it's just described by a unital star homomorphism from the linear operators on the smaller space onto the linear operators of the bigger space. For now, it's completely irrelevant what that means, and if you don't know what the unital star homomorphism is, doesn't matter, because if you do know, you still will not understand why it's the right thing here. But it's just the thing that works out. There are some extra subtleties in the infinite dimensional case related to continuity and so on. But how do we interpret such a function? Like, why is such a function with suitable properties in any way a reasonable description of a register? Well, the interpretation of this is, given any operation on the content of the register, we want this function maps u to xu, which is the corresponding operation on the whole register. So if I say apply u on the register x, I just evaluate x at point u, and this gives me the operation on the whole y. But it turns out that from this thing here, I can reconstruct also many other things. So for example, if I say I have a measurement on the register, I can also, from this function, determine what would be the measurement on the whole step. And this definition also allows me to chain registers, so one inside another, which is quite simple, that's some composition, but also make pairs, so I can show that if x and y are registers, there's a meaningful notion of the register x and y together. This one is not trivial, but you can show that it exists and has the properties we want. So this is very nice, and but I would like to show you, give you a very short idea why this is so nice. So I will show you like a proof in this formalism. I mean, a sketch to give you the idea. So we had in the in the verification condition earlier, we had this thing that we said we had a Hadamard on register R1, and then multiplied with a Hadamard on register Q2, and this multiplied with the intersection of Q1 R1 being equal to EPR. I mean, this thing here is actually also some syntactic sugar that means a subspace, and the subspace that these variables have this particular state, but I don't want to go in that, intersected with the analog thing on the other side. Yeah, and now I want to reduce this to something which is just involving matrices and not involving all these magic register formalisms. I can do that by just using the various properties. So this thing actually can be rewritten because, for example, the variable R1, that is one of the many variables in the first system, can be written as the register 1. So if I have a two-partite system, the left system, there is a register that just says out of the big memory, out of two memories, the left memory, and in this subregister 1. So this is just equivalent to just saying R1. Yeah, so it's the R1, like if I have a big system with two parts, and here I have R1, then I can also just say, well, I first take the register that's called 1, and inside that, the register R. That's the same as R1 in the big system. So I can rewrite those things correspondingly. So I can write 2.q, then type, and here these things I can also rewrite. So this is actually in register 1, so in the first half of the memory, subregister QR, which is the pair of Q and R. It's the same as, so that's the same as making Q1 and Q2 and then pairing them. So that this is equal to EPR and intersected with the same thing, QR is equal to EPR. So here's already something nice happening because this thing down here, I now formally see that they are on different memories, but in the same class. Before Q1 and Q2, they are formally not related in any way. They're just all different variables. But in this case, I see it's just in the first and second memory, I have some register which is the same on both sides. So that's already nice because it may help me for applying rules that make use of these things.
What does it mean to be the same thing inside now?
What it means in this case, I have, for example, the variable q. Imagine it refers to the fifth qubit. And now the fifth qubit, so if I look at the whole memory, let's say I have 10 qubit memory. So Q1 would be the fifth qubit, and Q2 would be the 15th qubit.
Yeah.
So it's kind of unrelated. But if I see it as Q1 is the fifth qubit out of the first half, and Q2 is the fifth qubit out of the second half, now suddenly I have this word, the fifth, on both sides appearing.
But how does it help us?
It helps us whenever I have some rule that says if I do the same thing on both sides, for example, I keep equality. So, I mean, in this step, it didn't help us yet, but it's already good to kind of be able to have these things honestly on the table and not just intricately. Yeah. Okay, now I can do rewriting things. So, for example, I have this and this are all on the first memory. So I can actually pull them into, so this product, I can pull together and say it's a product H on R applied to 1 times QR, applied to QR equal EPR, which is a space. What happened here? Why is that? Oh, no, it's not that. Okay. This thing, but inside the first memory. So I can use the different laws to rewrite it in this form. And that intersected with H on Q. And this on the second memory. So I can do rewriting things like this, which is nice because now I'm making the expression, this product here, simpler. And I can make it even simpler because I have that, no, not this one. This thing, okay, let me first copy it to the second page. So now something like QR is actually also the same, no, not QR, R is actually the same as the pair QR, and out of it, the first component. So I have in both cases a QR outside, so I can write this as H times, no, H on the first register times EPR, and the whole thing inside QR. And here, analogously for the second register, because, sorry, no, this is QR2 is R, so I get a 2 here, and here a 1.
That one at the outside.
Yes, I lost it. 1, 2. So, and I could also wrap these things now into 1 if I wanted, but I don't need to do this calculation. And now this thing that is written here is actually something elementary because lifting through a first, second kind of register. So this is actually just identity tensor H. well, actually not the whole thing, this part by definition. And this is H tensor identity. So now we have rewritten this into something that inside does not involve any of these pointers, but it is inside, but we have kind of at the end of the formula, we are saying where this thing is in the memory. And well, now these two things here, they are just matrices. We compute them and we see they are equal. I mean, that's specifically because it's EPR and Hadamard, and this is the same thing. So they are equal, and let's just call them psi for the moment. So what we get is we have psi in QR in 1 intersected with psi in QR in 2. And this thing now is actually, it says I have some state in QR on the first side, the same state in QR on the second side. And now it is just some generic lemma that holds no matter what register is written here or what state is written here, that this is actually implying that QR on the, okay, QR inside 1 is quantum equal to QR in 2. So this would be just a general basic fact about quantum quality. And this is just Q1 R1 equal Q2 R2. So I mean, this was a lengthy calculation, but it shows, I think part of this can also be automated, which is work in progress, but it shows that like all these things, we would never have been able to reason in this algebraic way about the registers if, about the variables, if Q1, Q2, R1, R2, they would be treated as different names. We can't kind of like focus on subparts and so on. So all this is enabled by the register formulas. Okay, I'm actually kind of out of time, so let me, well, but are there any questions about the register formulas? Okay, so then let me quickly say about the other things. There I will not go into any details. So there's also an Isabelle Holl backend. It allows us to reason in any arbitrary way about the verification conditions, which I showed you as a very quick example here. Yeah, we proved some lemma that we needed just in Isabelle, but also long-term goal is to have everything fully formalized in Isabelle Holl, so that we don't need to trust any of the implementations of the reasoning rules and so on. This is not there yet. What do we have in terms of formalization? We have a complete formalization of a relevant part of the theory of complex bounded operators. So this one is fully finished and on the archive of formal proofs. We have a formalization of registers. However, it is still only for finite dimensional case, because for the infinite dimensional case, we need some more topology, because it turns out that for the infinite dimensional case, you suddenly need things like trace class operators, big star topologies, and all these things. And they need to be first developed, but it's work in progress. Also, the registers are not used in the Qrihl tool. So the magic I just showed you on paper will not work at the moment, but I have a fork where it's partially implemented, but first the registers themselves need to kind of be implemented and so on. So also work in progress. Then the theory of tensor products. We have the theory of tensor products for the finite dimensional case, but it's not enough. And the infinite dimensional case is work in progress. again, there's like all this topology stuff and about, because we need to define the tensor products of for Neumann algebras, or well, kind of in this specific case, the tensor product of bounded operators, and that one is actually defined as you take all the products, the elementary tensor products of like two operators, which are easy to define. Then you take the linear closure, which is also easy, and then you take the closure in the strong operator topology, and now suddenly you involve topological things that you didn't want to do, but can't help it. And formalization of the semantics of QRHL and the logic itself, completely missing. However, this is mainly because this math stuff here is not there. I think that once these things are there, this one will not be too hard. So I think it's the math basics that are the hard work here. Yeah, and when it comes to proofs in the Qrihl tool, what have we done? Well, some small examples. The Fujisaki Okamoto variant that I mentioned, and we have work in progress working on compressed quantum oracles, which is some really fancy high-end post-quantum crypto technique. So I'm quite excited about getting this to work because it shows that you can really do not just the basic stuff, but also the stuff that actually no one understands. Because the compressed oracles is something that is really difficult to understand, and that means that if we can just formalize the proofs in the like formally, this gives us this is nice because then people don't need to understand the technique to be convinced that the proof is there. Yeah, and of course we want more like preferably all the final list standardization thingies, maybe some actual quantum protocols, that quantum key distribution and so on. Yeah, we want automation, module system, maybe something to import easy crypt proofs if they are already done, to kind of just add the quantum parts or something like this. Yeah, and if there's someone in the audience that isn't already here, you can apply here. And that's all I wanted to tell you. Any more questions? No questions? What about the remote audience? The remote audience was very quiet, but maybe there are any questions. Okay, then thank you for your attention and see you next time.